Today we start about linear operator, one important topics in functional analysis. We start functional analysis. Now we start the definition of linear operator. Okay, operator. First we start about operator. Which one is called operator? A mapping from a linear space to another linear space is called an operator. Okay, now we're going to this linearity of the set. That means to start in this way, let X be a set. Let X be a linear space over K. Let X be a linear space over K and C be a set. And let C be a set. So then C is a linear subspace. Then C is a linear subspace of X if C is a linear subspace of X if first one C is closed under addition. That means xy belongs to C implies that x plus y belongs to C. And number 2, C is closed under scalar multiplication. Okay, then alpha belongs to K and x belongs to C implies that alpha x belongs to C. Okay, now we're going to discuss about one topic, which is the definition of linear operator. Simple linear operator. That means first we talk about operator and then we talk about some linear subspace. Okay, now we discuss about linear operator. Okay, let xy be linear space over the same field K. Let xy be the linear spaces over the same field K. Then and tx to y an operator, then t is said to be a linear operator. If we erase the above portion, and we write or discuss about these things, then a linear operator if first one t is additive. Okay, additive means that is tx plus y equal to tx plus ty for all xy belongs to x. Understand? Next, second portion, one easy and simplest one. We just write T is homogeneous. Okay, T is homogeneous means T of alpha x equal to alpha of Tx, where alpha belongs to k and x belongs to x. Understand? Then if these two property hold, that means T is additive and T is homogeneous, then T is called a linear operator. Okay, an operator T is called a linear operator. A operator means a mapping from a vector space to another vector space, or a linear space to another linear space. Okay, so we erase these things or these portions. Now we discuss about some functional, linear functional. Okay, linear functional. Linear operator means one mapping from a space to another space, vector space. But linear functional means just if y equal to some field, then 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 a linear operator, then a linear operator tx to y, that means be a linear functional, another way, any map t to k be a linear functional. Okay, so next we discuss about some observations, that means some property. If tx to y be linear, if tx to y be linear, then some property are hold. First one, t0 equal to 0. Second one, t of minus x equal to minus of tx. Next, third one, t of x1 plus x2 plus dot 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 xn equal to t of x1 plus t of x2 plus dot 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 t of xn. Okay, next fourth one, t of alpha 1 alpha 2 dot 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 alpha n x equal to alpha 1 alpha 2 dot 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 alpha n dx. Okay, so these are the some property of a linear operator. Okay, then we discuss about these things, but we first talk about some example. Okay, now example, let x inner product be an inner product space. Okay, over R, and let A belongs to X. Then define Tx to R, define Tx to R by, define Tx to R by Tx equal to inner product of Ax, where A belongs to K and X belongs to A. A belongs to R and X belongs to A, and this one obviously belongs to R. Okay, then T be a linear function. Okay, next we're going to another example. So simple example, we're going to this. Now x equal to L2, we construct x equal to L2 with inner product xy equal to x in y in bar n equal to 1 to infinity. Then x equal to xn and y equal to yn belongs to L2, and diff a equal to a1 a2 dot 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 an belongs to L2. Then define t x to r by tx equal to a1 x1 a2 x2 dot 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 an xn plus dot dot dot. Okay, then this one obviously inner product of ax and less than equal to norm of x norm of a. Then t is a linear functional. Then t is a linear functional. Okay. Now we're going to next example. Okay. Example of some linear functional and linear operator. We're going to next example. Differential operator. Differential operator, we construct x equal to c1ab and y equal to cab. That means continuous functions from a closed interval ab, and c1ab means continuously differentiable in closed interval ab. Then define t x to y by tx equal to x dash of, that means t for x belongs to x dash means tx equal to dx by dt for x belongs to x. Okay, here obviously x is the function of t and here t. Okay, then t also a linear operator. Then t be a linear operator. How we prove this? We see that t is additive and also t is homogeneous. Then t is a linear operator. We not calculate or not operate this one, but just we see that. Okay, or we'll give some example. This one is called differential operator. Okay, this one is called differential operator. Now we also take one example, which one is called integral operator. Okay, integral operator, or simply this one is called integral functions also. That means we talk about x equal to rab, Riemann integral ab, and then define t x to r by tx t of f equal to integration of a to b f t dt. Okay, f belongs to rab. Then this one, then t be a linear functional. Then t be a linear functional. Okay, now we also discuss another one, but we give one example which is not linear operator. Okay, we give one example which is not linear. This all are linear operator. So we give some example of linear operator. Now also we keep one example which is not linear operator. X equal to c equal to y, and obviously k equal to c. Then we define define Tx to y by T of z, that means T of x plus iy equal to x, that means real z. Okay, otherwise this one is right, real z. Okay, and then we check about that this one is linear operator or not. First note that T of z1 plus z2 equal to T of x1 plus iy1 plus x2 plus iy2 equal to T of x1 plus x2 plus I of y1 plus y2. This equal to x1 plus x2, that means T of z1 plus T of z. Then T is additive, not a problem at all. Z1 Z2 belongs to x. But next portions, for alpha belongs to C, then T of alpha z equal to T of a plus ib multiplied by x plus iy. Then this one equal to T of ax minus by plus I into bx plus ay. This equal to ax minus by, not equal to tz, alpha tz. Okay, because alpha tz equal to a plus iv into x. This one not equal to, so T is not homogeneous. So T be not homogeneous. Hence T be not a linear operator. Okay, understand? We all understand these problems. Now we're going to further example, not further some definition, domain and range of some mapping. Okay, we know about that, but we also discuss here because this one is the one common thing of an operator: domain and range. Domain and range. So how we discuss, let x be two non-empty set, let x be y not equal to far be two set. Okay, then let tx to y be a mapping, then domain of t denoted by dt is a subset of x, for which t is defined, okay. Then dt equal to, in this way, in this form, x belongs to x such that tx is defined. Now the range of t is denoted by rt and is defined as rt equal to t of x such that x belongs to dt. Okay, so we discuss all these things or definition of domain and range. Now further proceed. T is or one map T is 1 1 means T is 1 1 implies that Tx equal to Ty implies x equal to y. Otherwise, x not equal to y implies that Tx not equal to Ty. Both are implies T equal is 1 1. Okay, and T is on 2. T is on 2 means Tx equal to y. Okay. Oh, sorry. For all yt there exists a x. That means rt equal to y. Rt equal to y. Okay. Understand? That means here for a y there exists a x. There for y there exists a x such that this one hold, but t is on 2 means rt equal to y. So this one and t on 2 means t is surjective and t 1 means t is injective. So t is bijective is both hold. Now we discuss about car t or null set. Okay. Now discuss about car t or null set. How we discuss? We first talk about definition of car t. Definition of car t or nullity of t. Let t x to y be a linear operator with domain t. Let t x to y be a linear operator with domain dt. Then the null set of t. Then the null set of t denoted by nt or car t is defined by nullity of t equal to x belongs to dt such that tx equal to 0. Okay. Next, we'll discuss about some propositions, some important propositions. Okay. We'll write the statement of these propositions. Let x, y be two linear spaces over K. And let Tx to y be a linear operator. With domain dt. Then first we have to prove that Rt be a subspace of y. And second we prove it nt is a subspace of x. Nt be a subspace of x. Okay. How we prove it? We prove so simply. We prove it just a subspace. We know about that. Which one is called subspace? We're going to these definitions. Definitions tell about that if C is closed under addition and C is closed under scalar multiplication, then C is called linear subspace of X. If C is subset of X and C satisfies those two properties, C is closed under addition and C is closed under scalar multiplication, then we call this one. So how we prove it? We prove in this way. So simply we first talk about Rt is a subspace of Y. We take y1 y2 belongs to Rt. Okay. Then we have to show that to show that to show that we do it directly. So alpha y1 plus beta y2 belongs to RT, where alpha beta belongs to K. Understand? So we have to prove this one. We have to prove this one. Then we done. RT is a subspace of Y. So what we do it? How we do it? Since y1 and y2 belongs to RT, this implies that then we have y1 equal to tx1 and y2 equal to tx2, where x1 x2 belongs to x. Understand? Or x, sorry, here we write dt beta. Okay, then obviously alpha x1 plus beta x2 belongs to dt. Okay, because dt is a vector space. Because dt is a vector space or linear space. Okay, then this implies that t of alpha x1 beta x2 belongs to RT, and this one equal to how much? By linearity, which says that t alpha x1 plus beta x2, then alpha y1 plus beta y. Then this, so t of alpha x1 plus beta x2 belongs to RT. This implies that alpha y1 plus beta y2 belongs to RT. This implies that RT is a subspace of Y. And again RT subset of Y. So RT be a subspace of Y. Okay, we prove it now. Next we discuss about NT. Okay, NT be a subspace of X. How we prove it? We prove it so simply. We just do it. We take x1 x2 belongs to NT. Okay, this implies that tx1 equal to 0 and tx2 equal to 0. Then, so simple way, we talk about alpha x1 plus beta x2. Okay, alpha x1 plus beta x2. Then to show this one, alpha x1 beta x2 belongs to NT. Then we talk about t of alpha x1 plus beta x2 equal to how much? Here alpha t of x1 plus beta t of x2, then alpha and multiplied 0, beta multiplied 0 equal to 0. So we see about that t of alpha x1 plus beta x2 belong equal to 0. This implies that alpha x1 plus beta x2 belongs to NT. So there for here for arbitrary alpha beta belongs to K. So NT be a subspace of X. Okay, understand or not? I think all are done. Now we're going to further. Okay, we're going to further discussions about linear operator. Now we going to one propositions, or no, we discuss about two definition of inverse mapping. Okay, whose mapping, that means is called inverse mappings. Let xy be two set, let xy be two sets, dt subset of x to y be a mapping then then the inverse mapping first inverse mapping T inverse rt to dt exists if t is injective. Now to inverse mapping T inverse y to dt exists if t is bijective. Okay, so we discuss about how one mapping inverse is exist. Now we also give some propositions about it. Okay, one important propositions about it we also discuss now. So these propositions tell about that let xy be vector spaces, let xy be vector spaces or linear spaces, and t dt subset of x to y be a linear operator, okay. Then the inverse operator, then the inverse operator T inverse rt to dt of t exists if and only if tx equal to 0 implies that x equal to 0. Okay, so how we prove it? We prove it simply. Suppose t inverse exists. Suppose t inverse exists. This implies that t is 1 1. T is 1 1 means let x belongs to dt. Let x belongs to dt, then tx equal to 0 implies that x equal to 0. Because tx equal to t0 0, this implies that x equal to 0. Okay. Since t is 1 1, now next we discuss about further in our portion to erase now. Next we talk about conversely. How conversely this one holds. That means tx equal to 0 implies that x equal to 0 holds. Okay, then we have to show that t is 1. We have to show that then t inverse exists. We have to show that t be 1 1. Then t inverse exists. How we show it? How we show it? Let x y belongs to dt. Okay, then tx equal to ty implies that this implies that tx minus ty equal to 0. This implies that t of x minus y equal to 0. This implies that this implies that by given condition x minus y equal to 0, this implies that x equal to y. So t is 1 1 by a given condition. So we prove it. T is 1 1 means we write about it. T inverse rt to dt exists. So we search about that If x y be vector space and t dt to y be a linear operator, then the inverse operator t inverse of t exists if tx equal to 0 implies that x equal to 0. One important assumption or one important result, okay, of linear operator. So today we stop here.